So 2 years ago, I took a vector analysis class, and I was dealt a question that I ultimately got 0 out of 10 on. Um, it's I'm looking back at it now, and I feel like such a dumbass. Like I felt like I should have been able to answer this. So I went back in retrospect a week ago, and it took me about half an hour before I finally realized the answer. So here we go. On the final exam, there was a question that went like this. Find all lambda that are real numbers such that negative y dx plus x dy over x squared plus y squared to the power of lambda along a curve C is equal to 0 when C is a simple closed curve in any simply connected region D that does not contain the origin. Part B, for the values of lambda found in A, evaluate negative y dx plus x dy over x squared plus y squared to the power of lambda over the curve C, where C is the unit circle. And part C is, does the answer in B contradict your finding in A, and explain? I'm going to put a question mark here, but yeah, I'm not going to write explain. So the way we do this is actually through Green's theorem. Now, as you know, through Green's theorem, I'm just going to simply recap it. Green's theorem states that if you have a region D, if D is a closed surface, if D is a closed surface, continuous, and positively oriented, then P and Q have continuous first order partial derivatives in D, then you can use an equation that looks like this. Then it's like C PDX plus QDY is equal to dq dx, partial dq dx minus dp dy dA. And don't try to make sense of it. Like I'm not here to explain theorems. Accept it for what it is. Like you'll learn math quicker this way. Trust me. So this is the and well, we can in fact use this formula because as you see, there's a simple closed curve. I should have wrote simple here. The curve is like, it's closed, so it's obviously going to be continuous, otherwise it wouldn't be closed. And it's positively oriented. It doesn't say that, but that doesn't really matter. You'll see why later on in this question, although they should have mentioned it. Okay, so in part A, I'm going to erase the theorem because I need the space. Green's theorem applies because the first order partial derivatives for P and Q are continuous in the region D, since all these curves don't contain the origin, so the first order partial derivatives will be continuous. So part A, we can use Green's theorem, essentially. The first thing I'm going to do, and it seems a little unnecessary, but I'm going to do this. Okay, so I'm going to rewrite this. Negative y dx plus y x dy over x squared plus y squared to the power of lambda. I'm going to rewrite it into something like this. This will help me organize my thoughts a little bit better. Negative y over x squared plus y squared to the power of lambda dx plus x over x squared plus y squared to the power of lambda dy. And then I can easily identify my p and q from here. So p is negative y over x squared plus y squared to the power of lambda. And q is going to be equal to x over x squared plus y squared to the power of lambda. All good? Okay. So obviously you would probably have to state the conditions of Green's theorem, but I'm not writing an exam, I'm just explaining to you the concept. So then this, we can simply use the, recall that formula, d, this is the one, what we're going to be using, dq dx minus dp dy, all partial derivatives, dA, okay? This is what we're using. So keeping this formula in mind, this value, of this integral is equal to, remember, D is any simply connected region, and you might get confused at first, but the answer is it really doesn't matter what this region D looks like as long as it doesn't contain the origin. If you really wanted to during the test, you could have like just mentioned that, like, you know, made up a region D. If you wanted to make it your own life easier, you could have said D was like a triangle that didn't contain the origin. This was like a straight line, like y equals x, and x was like 1 or 2, something like that didn't contain the origin. If that made you comfortable, you could have done that, but I figured it, but you really don't need to know what the value of D is. I cannot stress that enough. I think the ambiguity of this question was what got some people, in my opinion, even though the question actually is not that hard. Okay, so we'll make this D, you know what? I'm gonna make this D a little nicer. It doesn't look that much better. Okay, so then we have this. Let's just apply this formula in here. So that is equal to, now we just take the first partial derivative of q with respect to x, and that is equal to x squared plus y squared power of lambda minus, take the derivative of the denominator with respect to x, lambda x squared plus y squared lambda minus 1, so the lambda minus 1 times 2x divided by, you need to square the denominator, so x squared plus y squared, I'm just using the quotient rule, to the power of 2 lambda. Now, we need to minus dp dy, but minus becomes plus, so I'm just going to write a plus here. And okay, so we can imagine we take away this negative sign, so we have x squared plus y squared to the power of lambda again. Let me think. Minus y times lambda x squared plus y squared, lambda minus 1 times 2y over x squared plus y squared to the 2 lambda. So all I did was take the first partial derivatives of x and y respectively with q and p, applying this formula. That's just concept of using the first partial derivatives, first order partial derivatives. Normally one should cut the video like until they simplify, but I think the simplification is so elegant that I'm deciding not to cut any part of this video. If you wanted to, you could just skip to where the simplification occurs anyway. So yeah. Okay, it might be boring or fun depending on how you perceive math. I personally think this part's fun. Okay, so let's combine the these like terms in the numerator. Okay, so this will be equal to 2, because x squared plus y squared, x squared plus y squared, 2x squared plus y squared to the power of lambda, minus 2, let me think, minus 2x, because minus, yeah, x times 2x is 2x squared, so minus 2x squared lambda times x squared plus y squared lambda minus 1, and minus 2y squared lambda, x squared plus y squared to the power of lambda minus 1. Don't forget the denominator. All of this divided by x squared plus y squared to the power of 2 lambda. Crap. I should have written a dA there. I should have written a dA here. I forgot it. Slipped my mind. I'm not going to erase the whole thing. That would take forever. Okay, you know what? dA. Okay. Okay, so we have that there. And then when you do this, okay, so you can factor out lambda here, lambda times x squared plus y squared to the lambda minus 1. And let me just write it down. Okay, so d 2x squared plus y squared to the lambda minus, let me think, right, minus 2, you could see this for yourselves, x squared plus y squared times x squared plus y squared to the lambda minus 1 times lambda. Okay, yeah. Divide all of this divided by x squared plus y squared to the 2 lambda dA. And this times this just gives you lambda. So this is equal to d 2 x squared plus y squared. This is really boring for you guys. I'm really sorry, but cut it later into the video if you want to skip all of this simplification. 2, this is just x squared plus y squared to the power of lambda. Lambda times lambda divided by x squared plus y squared to the power of 2 lambda dA. And you can factor out this x squared plus y squared to the lambda in the numerator, and dividing that by the denominator gives you d, okay, all you get is 2 minus 2 lambda over x squared plus y squared to the power of lambda. Now, the reason why, and this is all equal to 0 as stated in part A. Now, the reason why it really doesn't matter what the region D is so long as it doesn't contain the origin is because if the only possible way for this line integral along the curve C to be 0 is when the integrand itself is equal to 0. So this 2 minus 2 lambda over x squared plus y squared to the power of lambda has to be equal to 0. That's the only requirement, regardless of what the region D looks like. And as you know, the way for this to be 0 is if the numerator itself is equal to 0. So 2 minus 2 lambda is equal to 0, and that means lambda is equal to 1. So that's the answer. The answer is lambda equal to 1 for part A. I'm just going to erase everything I did for part A, and let's move on to part B, keeping in mind that the answer to A is lambda equal to 1. All right, so part B asks us like for all the values we've obtained for part A for lambda, well, now we have to evaluate this along the unit circle. So applying this, c negative y dx plus x dy over x squared plus y squared to the lambda. I'm going to take a second to just consider the unit circle here. Let's draw out the unit circle. We can suppose it's positively oriented, even though the question doesn't say that. That's the ugliest circle I've ever seen in my life. Okay, so I'll just put a 0 here, 1 and a 1. Okay, so x is equal to cosine t. Use the parameter t where t is a real number. Y is equal to sine t. T is a real number. And from the unit circle, like a full revolution of the unit circle is from 0 to 2 pi. So basically, this is equal to, or using our parameter t, it's from 0 to 2 pi, negative y dx. Actually, I should have mentioned this on the side. So dx is negative sine t dt, dy is cos t dt. So yeah, like let's just plug in the values and then all turn them into just the parameter t. So yeah, t equals 0 to 2 equals 2 pi. Negative y, negative sine t times negative sine t dt, plus cos, yeah, so x is cos t times cos t dt over x squared plus y squared is just 1, like because sine squared t plus cos squared t is just equal to 1. So this is just equal to, from 0 to 2 pi, we could eliminate the denominator actually. Factor out the dt, sine squared t plus cos squared t dt. This is equal to 1. 1 times 2 pi is 2 pi. So the answer for part B is 2 pi. Now, at first, now this is different from our answer in part A, which is 0 when lambda is 1. But keep in mind that we are doing enclosing this around the unit circle, and the unit circle includes the origin. So it actually violates Green's theorem, essentially, because there's this tiny point where my pen is right here, a tiny point in the origin where like the partial derivatives for P and Q are not continuous, like it's not differentiable at 0, 0. So Green's theorem does not apply for part B. So this is not a contradiction since we're in two different scenarios. So since part B does not involve Green's theorem, this is not a contradiction. And it actually doesn't, the question, like I said earlier, should have mentioned that the curve is positively oriented, but that doesn't really matter because if this was negatively oriented in part B, you would have had simply a negative 2 pi as opposed to a positive 2 pi. And that's still different from zero, your zero value in part A, so it doesn't really matter. Regardless, you're going to get different values. So yeah, that's all for this video. I'd love to stay, but for now, I gotta jump. I'll see you guys on the other side of the bridge. Catch you next time.